So hello everyone again, and thank you for joining us for our newest informational webinar. This one is about DNS high availability tools. As said before, my name is Dagmar and I will be your facilitator today. And with me is Karsten Strothmann from the Men&Mice Professional Services team. And he will be giving you all the insight on the DNS high availability tools today. We will be taking questions during the webinar. So if you use the questions functionality of the GoToWebinar, I'll collect them and submit them to Karsten at the end of the webinar. Please note that all attendees are on mute and that we are recording the session, and you will find the webinar along with the slides at our website in the next coming days. I will also make sure to email this your way. So without any further ado, I'll hand this over to you, Karsten.
Thank you, Dagmar. So hello everybody for today's webinar on DNS high availability tools. I have a lot of information for you, and this is about what we can do to make especially DNS-Resolvers high available. So we talk about the DNS-Client part and how Windows and Linux and other Unixes like macOS, iOS choose the DNS-Server among the list of available servers, and how we can make a DNS-Resolver service more failure-tolerant with DNS-dist and relay D. But first, we talk a little bit about the authoritative DNS side. So in my work as a professional consultant for Men&Mice, I sometimes see customers deploying load balancers in front of authoritative servers. While there might be situations where a load balancer in front of an authoritative server is really useful, very often it is really not, because the DNS protocol has load balancing and high availability built in the protocol itself. And before we look at the resolver part, I would like to show you a little bit about how that works. Now, on this picture here, we have on the in the lower right corner, a client machine that will send a DNS query. On the lower left side, we have a DNS-Resolver or a caching server. And on the top, we have three root name servers, A, B, and C root name servers. Now, what I will show you now is true for all the DNS servers, for all authoritative servers on every level. It's not only for the root name servers, it also works for the TLD servers and any servers below that level. The little blue table that you see on the upper left side is a table that lives inside the DNS-Resolver on the left side. It's a table that is in every DNS-Resolver. So whether you use the bind name server, Unbound, or Microsoft DNS as a resolver, all these products have basically the same configuration and algorithms built in. Upon start, this table contains the DNS server known to the resolver, and a DNS server knows the root name servers by loading the root hints file. And in this table, we have in a second column the Roundtrip Time value, and by default this value is seeded with a very low number. Now our client is requesting the domain name ftp-men&mice.is. Query goes out to the DNS-Resolver, and that DNS-Resolver doesn't have the delegation to the Icelandic top-level domain in its cache, so it needs to go to the root name server. And now, whenever it needs to go to a name server where there are more than one choice for the zone, so a zone that has multiple authoritative servers, it will consult, the DNS server will consult this table and will choose the server with the lowest RTT number, the lowest round-trip time number, which is the A root name server in our example here. So query goes out to the A server, no, sorry, to the C server, sorry, because that has the value of 2, and the answer is coming back with the referral, the list of the name server authoritative for .is. And the actual communication round-trip time is being filled into that table, which is 338 in this example. We skip the rest of the communication and skip forward to the next request, which goes out for www.yahoo in France. Now, the .fr top-level domain is also not in the cache of the resolver, so it needs to talk to the root name server system again. So it looks again into the table, and now the lowest value has the server A. Also, pay attention to what happens to the value in for C. It is 338 now, and after we get a request and an answer back, it has been decreased. So it's 331 now. The algorithm is that every server in the list that has not been used in a round is decreased by 2%. Now we see that the A root name server here has a lower round trip time, so answers are flowing faster from the A root name server. It's just 85. These values here is just an indication of the round trip time speed. It doesn't have any scale, so it's not hops or milliseconds or anything else. It's just a number that shows the round trip time, the relative speed of answering of the servers. We skip forward again, and now the client is asking for the ns.berkeley.edu name. And .edu as a top-level domain is also not in the cache of our server, so it again needs to go to the root name server system, and it will choose the root name server B in this case because it has the lowest number. Again, the values for A and C has been decreased by 2% now, and the round-trip time number for B is filled in, 350. And now we see that from the three name servers, A name server is the fastest one and will be used for all the next queries that go out to the root name server system. While all the queries go to A, B and C will be decreased by 2% and eventually will be lower than 83 and then will be queried again. If they are still slower, they will be pushed back again. If they, for whatever reason, better hardware, better networking, get faster, they will be climbing up to the first spot of the table and will be used there. So with this algorithm, the DNS protocol can easily load balance among multiple servers. If one server goes completely out of business, we will get a timeout value, which is a very, very high round-trip time that will be filled into the table, and that will effectively blacklisting that server for multiple minutes, depending on the query rate to that zone. If the server later goes into business again, it will be probed again, and if it answers, it will go back into the pool of servers to be used. And if you need to distribute more load because your existing servers for a zone have too much load, you can just add more name servers, more NS records to your zone, and load will automatically distribute among all the available servers. Now let's look at the Stub resolver side. On the Stub resolver side, it makes much more sense to have a load balancer, and I will show you why. Now, on Unix and Linux Stub resolvers, the configuration is stored in a file called resolve.conf, and that's usually in the etc directory. And in the etc directory, in that file resolve.conf, we have up to 3 name server declarations, each with the keyword name server and then an IP address, which is the IP address of a caching resolver to ask. And the IP address can either be an IPv4 address or it can be an IPv6 address. If there's multiple name servers listed, they are all created in the order given, meaning that always the first in the list, the first in the file, will be created first. And the operating system resolver has no cache. It has no memory. It does not know if in a previous request the server was unavailable, so it will always ask the first server, even if that is gone. The second server and the third servers will be used depending on the timeout values and the number of DNS resolvers being configured in the resolve.conf. Modern Linux systems try 2 times to resolve the name for each server. And if we just have one DNS-Resolver configured, it first waits 5 seconds and then it waits 10 seconds, a total of 15 seconds. If there's no answer from either name service, or from the one name server in 15 seconds, it gives up and gives an error message to the application. If we have 2 resolvers configured, it sends the query to the first server, waits 5 seconds, sends it to the second server, waits 5 seconds, then does that again for the second attempt. So we have a total timeout of 20 seconds. And if we have 3 DNS resolvers configured, then we send a query to the first one, wait 5 seconds, the second one, wait 5 seconds, the third one, wait 5 seconds, and then do the same again, but this time in the second round only wait 3 seconds. So we have a total timeout of 24 seconds. On a Unix DNS resolver, the timeout can be changed in the file /resolve.conf with the option statement. So we can specify the number of seconds that we want to wait and the number of attempts that should be done, should be queries sent per each server. So in this configuration we see here, we have 2 servers configured. We wait just for 1 second on every turn, and we have 4 attempts. However, the timeout only specifies the initial timeout, and all the next timeouts for the second, third, and fourth attempt is always the double of the initial timeout divided by the number of name servers in the resolve.conf. If we don't like the fixed order, we can have the option rotate in our resolve.conf, which will enable rotation. So in each resolver session, for subsequent DNS queries, not the first name server in the list will always be used, but the resolver will change between the first and the second. However, this is not globally system-wide, it's only per resolver session, per application. So only if the application opens the resolver session to the operating system resolver library and then sends multiple queries over that one session, we see this round robin in effect. If we have applications like Ping that just open one resolver session and then close it again and then reopen it again on the next invocation of Ping, we will not see the round robin because the application only does one query per session. So rotate is not as useful as you might think. The other big question is how to configure these extra options from a central place, because you don't want to walk around as an administrator, configure all your client machines. It is possible to distribute this information via DHCP, but there's no default option, no standard DHCP option that you can use. So you have to create your custom option. And I have an example here how to do that in the IC DHCP server. And once you have that in the IC DHCP server, then on the client side, we also have to tell the clients the option and add a DHCP script hook. So if you use off-the-shelf Unix systems like a Linux distribution, that will not help a lot because you would have to touch all installations and make this customizations yourself. On the Windows side, we have a similar picture. We can configure the DNS servers in the TCP/IP settings. We can either obtain the DNS servers by DHCP or we can configure them manually. There's the preferred and the alternative DNS server in the first graphical pop-up here, and if we click on Advanced button, then we have the possibility to add additional DNS resolvers to query in this list, and there can be a lot of them. However, don't put too much DNS resolvers in there. 3, 4, 5 is a good value. More is probably not very useful. If we have just one DNS-Resolver configured on Windows, the Windows operating system will send the initial query and wait for just 1 second. Then it will send a second query, wait 1 second, a third query, wait 2 seconds, then a fourth query, wait 4 seconds, then a fifth query, wait another 4 seconds, and then it gives up after 12 seconds in total. So it's just 2 seconds more than on the Unix side for one DNS server. If we have two DNS server configured, the algorithm looks a little bit different. So the initial query goes out to the first server in the list, and we wait 1 second. And if there's no answer after 1 second, there is another query sent to the second server in the list. We wait another 1 second. Then there's a second server to the second query to the second server in the list, and we wait 2 seconds. So only the second server is queried twice. And then on the fourth attempt, a query will be sent to all servers in the list simultaneously, and we wait 4 seconds. And then we send another time to all the servers in the list, wait another 4 seconds, and after 12 seconds in total, the client resolver gives up and gives an error message to the application. And with 3 or more DNS server, the initial query is sent to the first server, 1 second waiting time. Then another query is sent to the second server, another 1 second waiting time. Third query is the first query sent to the third server, wait 2 seconds. Then again, we send queries to all the servers, wait 4 seconds, do that twice, and we have again a total of 12 seconds. So on the Windows side, after 12 seconds, we have either guaranteed an answer from DNS, or we have a failure. These timeout values can be customized using a registry value, and I've linked here to blog posts from the Microsoft TechNet website, which explains how this value can be customized in the registry. However, it's not really recommended to do that because the original values are quite good, and they have been proven to be good. And if you have problems with your DNS-Resolver infrastructure, it might be better to make the resolver infrastructure more resilient. Now I've set up a demo environment here, and I've recorded some videos to show you the effect of a DNS server dying. I have 2 resolvers in the network. One is the IP address 210 at the end, and the other is the 217. And the resolve.conf lists both of them on the Unix side. So all the queries are sent to the first server initially. And only if that is not available after timeout, it sends to the second one. Now let's see how that looks like. So here we have the client machine on the top. And here we see we have in resolve.conf the 2 name servers configured, the 210 and the 217. And the 2 windows below are the 2 name servers, the 210 and 217. And I've written a small script that reads a file full of domain names to be looked up, and then the script uses the get-end command, a host with the domain name, to do a name lookup using the standard Unix resolver. Now I start the script and I pipe 10 domain names into the script, and the time command is timing how long it takes to execute the 10 DNS lookups. Now we see for the most lookups it takes just a few milliseconds. And there was one in the list which didn't resolve immediately because that domain has some configuration problems. So the total lookup time was 9 seconds, which is not too bad for 10 lookups. Now I will disable the first DNS-Resolver. And then we will redo the same experiment and see how fast the name resolution is from the client side. So the server is now gone, doesn't respond anymore, it's switched off. Only the second server, the one on the lower right side, is still there. And I call the script again, and we'll see that now every lookup will take 5 seconds plus a little. So this was 5 seconds, another 5 seconds. And we see on the lower right side, we see the query logging from the name server, and we see that all the queries end up on the 217 DNS server. And very consistently, every lookup now takes 5 seconds. Because a query is being sent to the defunct DNS-Resolver, the client operating system waits the 5 seconds, and because there's no answer coming back, it will switch over to the second entry. Now, querying 10 domain names took 50 seconds. So this is not good. If you have this problem in your network, your users will be quite unhappy because DNS browsing and working on the network would feel very, very slow. So what can we do about this? One option is to use OpenBSD's RelayD. Now, RelayD is a daemon that can relay and dynamically redirect incoming connections to a target host. It's available in OpenBSD in the latest version, and older versions can be found on FreeBSD. This special thing about RelayD is that it dynamically reconfigures the OpenBSD firewall, PF, to redirect the traffic. In addition to working with a firewall, RelayD can also work as an application layer proxy. So here is the setup with RelayD. We have our two DNS servers, and there's now a second IP address, the 206, that can move between the two machines. And the movement is being done with the CARP protocol, which is a server redundancy protocol, open source, which is part of OpenBSD. Both machines run RelayD and the DNS server. And in the resolve.conf, we have now the 206, the virtual IP address that is being controlled by the CARP protocol, have that as the first place in the resolve.conf, and we have 210 and 217 as the second and third option there. So queries go to the machine that is online, and if that is gone, it will automatically switch the IP address to the second machine, and all DNS queries will flow there. This is an example configuration for RelayD for layer 3 forwarding. So forwarding directly on the kernel firewall level. There's a table called DNS-Server, which contains the IP addresses of all the DNS servers we want to load balance. And then we have a redirect statement called DNS balance, and it tells RelayD to listen on the 206 IP address, both for TCP and UDP port 53, and forward all requests to the machines in the table DNS server and check for TCP port 53, check the health of the server. So this is how the layer 3 redirect with RelayD works. RelayD will probe the DNS server on port 53, and if it's okay, it will reconfigure the firewall rules to do a direct forwarding. And if a DNS query comes in, the firewall directly forwards that query to the DNS server running on the machine. If the DNS server is down, the probe is not okay, RelayD reconfigures the firewall so that the query will go to the other machine. In addition, also the CARP protocol makes sure that the IP address will move over if the machine completely fails. So like if the hardware is malfunctioning, or the machine is brought down, or there's a network disconnect. In addition to having layer 3 forwarding, RelayD can also work as the layer 7 application proxy. In this mode, it will receive the DNS query and will send a new query like a proxy to the servers. Configuration is very similar. We have the DNS server table with the 2 IP addresses. We define a DNS protocol called DNS Proto that makes the relay know that it will listen on UDP and TCP, and it gives RelayD a little knowledge about the DNS protocol. We configured the relay called DNS balance. It's listening on the IP address port 53, and it forwards to the table DNS server, and it will do the check over TCP. This is how the layer 7 proxy works. The probe checks, and there's no reconfiguration of the firewall. If the DNS query comes in, that query goes directly to RelayD, because RelayD is now listening on port 53, UDP and TCP, and the query is being forwarded to the DNS server running on the same machine, if that is alive and working. If it's down, then the query will be directly forwarded to the DNS server on the other machine. And here we have a demo how RelayD works. So this is on the OpenBSD machine. Here we have the layer 7 configuration on the OpenBSD machine. We have the protocol defined and the relay configuration. Now I'm starting the RelayD daemon in the foreground, that is debug mode and verbose, so that we see all the communication going on. So it checks the 2 IP addresses and finds them, both are okay, both are up. And with relay control show hosts, it can get some statistics. So I see both machines are currently up and running. And on the top, I see the DNS flowing. This is back on the client machine with the DNS servers on the bottom. And here I'm running the lookup script again with both machines running. And there's one domain name here that creates a server fail. So we have a little hiccup in the resolution, but in total we have 12 seconds. Our total resolution time for 10 domain names. That is okay. The delay was because there was one domain name in the 10 that resolved into a server fail. So now I'm switching off the first DNS server, and we should see that message coming in here. Yep, we see that. So RelayD has now detected that host 172.22.1.210 is down. State went from up to down, and the availability is now only 87.5%. And now all requests coming to the OpenBSD machine on port 53 will be sent to the other machine, to the 217. When I look with relay control show hosts, I see now that the first machine is down, TCP connect timeout. The second machine is still up and running. Now in this situation, without the load balancer, we have seen that we have this 5-second penalty on every request. And here we don't have that anymore. It only took 3 seconds to resolve all the 10 names. Now I switch on the first server again. State went from down to up. Relay CTL show host tells me that the machine is up again. Doing the lookup again, and now it's even faster. It's just a half a second for resolving all 10 names. So the second tool that I would like to show you is DNS-dist from PowerDNS. And DNS-dist is a DNS-aware application level gateway. In that, it is very similar to in the basic working to relay when working in layer 7 mode, but it has much more DNS-specific features, which I will show you. DNS-dist is part of PowerDNS, but it is DNS-server agnostic, meaning you can use DNS-dist with any DNS server in the backend. It can be a bind, can be unbound, can be Microsoft DNS, can be, of course, PowerDNS. It has various load balancing schemes, so least outstanding, the first available, weighted hash, weighted random, round robin, you choose. And it can do much, much more than just load balancing. It can filter, block, rewrite DNS traffic. Have a look on the website and the good videos that are linked there to learn more about DNS-dist if you are interested. It has a Lua configuration. It is Lua scriptable, and it's available for most Linux distributions as a package for Debian, SUSE, Ubuntu, CentOS, and FreeBSD. And you should be able to compile it from source for any other Unix-ish system. So if you have OpenBSD, NetBSD, or a Linux that is not directly supported, shouldn't be a problem. It's free software with the GPL version 2 license, and the homepage is dnsdist.org. Now, how does DNS-dist work? It is a load balancer you put usually in front of your DNS servers. In a small configuration, you could also have DNS-dist running directly on your DNS servers as well. So here in my example, I have two DNS-dist machines having the IP address 172.22.1.200, and that IP address is also in the resolve.conf, and there's a heartbeat protocol running between the two machines, detecting if one machine is going down, so the other machine goes on and uses the same IP address. It's basically creating a cluster, a Linux cluster from DNS-dist. And then there's the DNS servers above there, and DNS-dist distributes intelligently the queries on the available DNS servers. And it does it so that it makes most use of the cache content. So it basically measures the latency of the DNS queries and responses, and then uses the server which has the least latency. Queries then go out to the internet and come back. Starting DNS-dist is very, very simple. Of course, you can write a complicated configuration file, but you don't need to. You can start DNS-dist directly on the command line, DNS-dist -L for local IP to listen on. So on the 1-200 we listen, and then we give as the other parameters the IP addresses of the servers where we want to forward the queries to. Here we want to forward to 210 and 217. And now we have a demo time with DNS-dist. So our first DNS server in this case is still defunct. It is switched off. And this is the load balancer machine where I will start DNS-dist, listen on the 200, and forwarding to 172.2.1.210 and 217. So DNS-dist is starting, it is probing the servers, and it's marking the first as down and the second as up. So this is consistent to the configuration. Now I'm switching over to the client again, and I'm changing the resolve.conf, putting in the 200 here, and removing all the rest. So all the queries go to this 200, which is the DNS-dist machine. And I'm starting here my little lookup script again. 10 lookups. Wow, that was fast. So that was just 0.4 seconds for 10 lookups. And the second time, it is again just even less than half a second. Now and remember, this was with the first server turned off. Now I switch on the first server. It should even get better. When I switch over to the DNS-Dist machine and look there at the console, it should tell me that the second machine is now up. Yeah, the 210 is now up. Tells me here. I'm doing the test again. And now the one query with the server fail respond that ended up on the empty cache one on the machine that just restarted. So it took here 10 seconds. That was 2 timeouts on one query. But on the second run of the script, we have again the very good result of under a second for all the 10 lookups. DNS-Dist also has some more options. It has nice statistics. So for example, on the console of DNS-Dist, I can query the top clients that send queries to this load balancer. In this case, it was just one client. I can also ask for the top queries. Here we see the 009.com, that was the one that created the serve fail. We had 10 queries for that one. We can also specify just the top level domains. Let's see, 82 queries for com, 4 queries for org. We can look at the responses. So this is all the serve fail responses. We have 3 serve fail responses from 009.com. Or we can look at the NX domains. This would be the NX domains, but there wasn't any NX domains in my testing. So we have there. And this is the top slow resolving names, which is again 009 and Fedora project. And DNS-Dist has even a built-in web server, which I can start from the console. It should listen on this IP address and should have the password. And it will launch a web server that we can now access from any browser. We can use any username, but the secret password. I'm going here in my browser, go to that IP address, port 80, 83, any name works, the super secret password. And here we are on the web console of DNS-Dist. It tells me the uptime, 8 minutes, number of queries, 86 queries received. And let me start the lookup again to see some graphs here. We see the query per second, server fail per second, and the cache hit rate on the bottom. The script still works, still hit the serve fail with 009. I'm starting here another script that does some more queries. And we see the statistics dynamically, automatically updating on the website. So how does RelayD and DNS-Dist compare? RelayD, it's only available on the BSDs. I would recommend OpenBSD because you get the latest version of RelayD there, but FreeBSD also contains RelayD in an older version. DNSdist, on the other side, is available for most Linux and Unix systems. So if you are not familiar with the BSDs, then DNSdist might be a better solution. RelayD allows the fast layer 3 forwarding directly in kernel space without touching user space at all. So that is a benefit if you need to have really fast forwarding in your load balancer. DNSdist only does user space proxying, but it is still pretty fast. The PowerDNS people, they say that they have tested it with millions of queries per second. So DNSdist is probably, with modern hardware, fast enough for most situations. RelayD only has simple health monitoring and reporting. DNSdist has much more. It has these online DNS statistics and it has the web UI statistics, which is nice. With RelayD, you have all the power of the PF firewall to filter. But with DNSdist, you have DNS-aware filtering with Lua scripting built in. So while you have with RelayD, you have more general options, with DNSdist, you have more DNS-specific options, which might be good if you need to fight certain kinds of abuse or certain kinds of denial of service attacks on your infrastructure. And the license, both is open source, but RelayD is BSD licensed, and DNSdist is GPL. Sorry, GPL version 2, not 3. It's an error here on the slide. So that was the content of today's webinar. Before we come to the question and answer session, let me quickly tell you about our ongoing trainings next year. We have the next training sessions, our DNS and bind hand-on and introduction and advanced in Redwood City in the ISC offices in February, and another session here in Europe, either in Amsterdam or Osnabrück in Germany on the March 6th to 10th. And we will have more webinars for you in 2017. In February, we do a webinar on Bind9 logging best practices. Then in March, we have a DNSSEC zone signing tutorial. This is for DNSSEC bloody beginners. So if you want to know how to sign a zone with DNSSEC, that is for you. In April, we have again an email topic, which is we will compare SMTP strict transport security with SMTP with DANE, because these are two competing standards that try to solve a security problem. And we will look into what are the benefits of either one or the other one. And we have more. We will later in next year talk about DNSSEC key management with the new Bind9 key manager tool. We will have a look on how to operate Bind9 and the Men&Mice suite on Docker on Linux. And we have the Men&Mice suite on Docker with Windows 2016 server. And we will look into how to manage DMARC, SPF, DKIM, multipart text records, CAA, DANE records in DNS zones, also with the Men&Mice suite and without. So we look into normal text zone files and how to use the Men&Mice tools to do that. We will talk about DNS over TCP and the new developments from the IETF and what to expect in the future. And we look into DNS-Server with SQL database backends, especially PowerDNS and Bind9. So a lot of new interesting stuff coming up. Now I'm calling Dagmar again. Hi, do you have any questions?
Yes, there is one question already here from Frank, but I want to encourage others, if you have questions, to leave them in the questions functionality here at GoToWebinar. But okay, I'll start with here. Frank, he asks, how does the open source load balancer compare to commercial load balancing appliances?
Yeah, I've seen some commercial load balancers in the past that do DNS, but not all. So what I say might not apply to all of them. But for most that I've seen so far, I had the feeling that these appliances were foremost built to do load balancing of HTTP and similar protocols, and don't really have much knowledge about the particularities of the DNS protocol. Especially, for example, with HTTP, it's important that you load balance requests to the least loaded server. While with DNS, you want to load balance all the traffic to the most loaded server, unless the round-trip time goes up. That is the answer time goes up. This is because of the caching. A web server or most other protocols don't do caching. But if you have a load balancer in front of a resolver, you want to make the best use of the caches. So you want to have as much traffic on a single machine that builds up a good cache. And only if that single machine cannot cope with the load, then you want to spill over some requests to the other machines. And DNS-dist does this because it has this built-in, this knowledge about the DNS protocol built in. But I haven't so far seen any commercial DNS load balancer that does this as well.
Okay.
Hope that answers the question.
Yes, I have a couple of more questions here. We have a question from Jeffrey Chung. He asks, do you run dist on 2 servers for high availability?
Yes, this was on the picture. Let me quickly scroll back if I find it. Here we are. So it's DNS on 2 servers, and there needs to be some mechanism outside of DNS-dist to make it high available itself. I've chosen here the Heartbeat system, which is a common Linux system to build clusters. It will basically check the health of each machine and take over the IP address if needed.
Okay, so I hope this answers his question, but we also have a question here from Peter Davies. He says, can dist handle server-to-server communication like notify and zone transfer?
Not to my knowledge. DNS-dist only works with queries, UDP and TCP queries. And also that is the purpose of using that. Usually with zone transfers, you can with common DNS servers, you can just specify multiple masters, and then the server will just try each of them. And the zone transfer is not as time critical. So if the zone transfer has a 5 or 10 seconds delay, that's not a big problem. 5 or 10 second delay on every request is a problem. So DNS is not built for that. Same for notifies. However, notifies being just normal DNS traffic should just go fine through a DNS-dist.
Okay. So, are there any more questions out there from our audiences? There haven't been more added, but we still have a couple of minutes if we need it.
I have one addition to the question from Peter Davis. About the notifies. While technically it would be possible to send notifies through DNS-dist, I recommend against it, because DNS-dist will only forward to one of the name servers. With notifies, you usually want to inform all your name servers of a change in a zone. So it's best to send the notifies directly to the name server's IP addresses and not to the DNS-dist addresses. Although it wouldn't hurt if you send it through DNS-dist as well, they should be sent also to all the other IPs.
Okay. Excellent. So I think for now, Karsten, if you have don't have more to add to this, we don't have any more questions from our attendees. I would actually like to thank everybody for joining us today. We really hope that you enjoyed this webinar. The schedule for the webinars for the year 2017 will be live on our website for signups in the coming days. Again, we will email you the recording and the slides from today's webinar, and we sure hope that you will join us in our future webinars. So thank you all for today.
Thanks for listening. Thanks, Dagmar.
Yes.
And greetings to Iceland.
Thank you. Take care, everybody. Bye-bye.
Bye for now.